Welcome to my channel on numerical methods in civil engineering. Like, share, subscribe, press bell button for latest update. Okay, in the today's class, I'll be just going through the method. So this is an introduction which I've given, and the Newmark method is applicable for finding bending moment, shear force, slope, and deflection for the complex loads. Okay, and so first thing is to find out the equivalent loads. So depending upon the type of the variation of the load, you need to consider the formulas. So these are the formulas which you're going to consider for linear variation of the UDL. I mean, varying load. Okay. And if it is a parabolic varying load, there's a complex loading on the beam. Okay. If you have a parabolic variation in the load, so these are the formulas which you're going to use. Okay. And you have the relationship between the bending moment, shear force load, bending moment, shear force, slope, and bending moment, deflection, and the slope. Okay. So this we have already earlier you have learned in strength of materials. Okay, these are the steps in the finding out the bending moment, shear force, and slope deflection by using Newmark method. So I was explaining step by step. Okay, let us consider a beam with the UDL. Okay, step one, the beam is divided into suitable number of segments. Okay, so that this way 1, 2, 3, 4, 5, 6 segments we have divided. So each segment is having an interval of h. Okay. Next, so if the according to Newmark's method, you can take these loads as W0, W1, W2, W3, W4, W5, W6, so on. Okay. And so the next step is to find out the equivalent joint loads, or equivalent loads actually, pivotal point load at pivotal points. So now let us consider the P0, P1, P2, P3, P4, and P5, P6 as the loads acting at the 0, 1, 2, 3, 4, 5, 6. Okay. What we will be doing is here we'll be converting the UDL into point loads actually. UDL. So in some case it can be a irregular load. Okay. It can be a irregular load that can also be converted into point loads, splitting up into equal intervals. So this is what we are doing now. So the step 2 is finding out the equivalent loads. Okay. Since the variation of the UDL is straight, and as you can see actually, so yeah, now let us consider this is the general case. Okay, general case. We need to consider P0. Now earlier it was okay. We have to consider such a kind of variation in the load, but in our problem, the UDL is a linear. It's a constant load. Okay, so it's a straight and constant. So therefore, no variation in the W0 and W. So it will be same only. Hence, we will be considering them as WWW only. Okay. So the formula for this case, okay, this kind of straight line variation in the load. Okay. For that, the formulas are given by starting load is equal to P0, which is equal to H by minus H by 6 into 2 into W0, which is nothing but the starting ordinate, and W1, which is the ending ordinate. Then the intermediate ordinates are intermediate concentrated loads are given by equivalent loads are given by H by 6 into W0 plus 4W1 plus W2, and this can be different. Okay, so for this intermediate, P1, it is W0 plus W1, W0 plus 4W1 plus W2. Similarly, if it is any one, okay, let us say P3. So P3 will be equal to H by 6, which is nothing but the H is the interval and 6 is the number of divisions. Okay, and are the formula actually, not division. So it's a formula, and for P3, W2 plus 4 times W3 plus W4. Okay, that way we need to calculate the equivalent loads at pivotal points in the beams, in the intermediate points. So starting and ending point will have same formula. So the last ordinate or last equivalent load will be h by 6, 2 times the last ordinate. Here it will be W6, and 1 time the previous ordinate. Okay, so that's nothing but Wn minus 1. So that's how we will be calculating the equivalent loads in the case of Newmark method. Next, so let us consider how to calculate P naught, I mean initial load.
Okay.
So as we can see, the so, so this is the beam which is loaded by UDL, and as you can see here, all W0, W1, W2, all values are equal to W since it is uniformly varying. Everywhere it will be W only. Okay, so W, 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 right? Now let us consider. Okay, so here now these P0, P2, P1, P0, P1, P2, P3 will be considered here. Okay, so therefore over here we'll have to calculate the load. Okay, yeah, we'll have to calculate P naught. P naught is equal to this formula. So you just need to substitute the W naught and W1. W naught is equal to W1 is equal to W. Just substitute them. So which is equal to yes, 1 second. So what do? You have to consider the starting load, and you know formula. Just substitute W and W naught and W1, which are equal to W and W. Just do that. If you do that, okay. So here is the portion we will be considering. So this is the portion. So therefore, the load will be finally you will get it equal to, so 2 times W plus W, it will be 3W. 3W by 6, it will be 0.5 WH. Okay. So that's how we will get the value of W. Okay. That's nothing but P naught. Now let us calculate P1. Okay. So in order to calculate P1, so what we need to consider is we need to consider this area. So both the three ordinates, I mean these three we need to consider. Okay, here is the one which is going to get the value of P1. Okay, so in order to get P1, so that is the formula. So because this is the range, okay, this is the range. So here W0, W1, W2 will get it. Okay, over here. So in this range, W0, W1, and W2 will be the values. So all values equal to W only. Just substitute all those things. I will get it as W, W, W. So it will be W plus 4W plus W, 6W. 6W by 6 will be 1W. Okay, so WH will be the answer, isn't it? So let us substitute them. And as you can see, so the minus WH will be the answer. Okay. Similarly, now let us consider the next range. Okay. So next range will be this. Okay. So P2 value, the value of P2 can be equal to, so because it is in this range from here to here, what are the values which will be there? W1, W2, W3. So those are the three values. So W2 will have four times value, and other two over here and here will be 1 time. So H by 6, W1 plus 4 times W2 plus W3. Okay. So that's how I will have to calculate. And if you substitute them, the value of P2 will be equal to minus WH. Okay. All of you understood, right? How we will be calculating the equivalent loads. Okay. This is how we do, right? Next, similarly, we'll have to calculate all the joint loads. Okay. All the equivalent loads at the pivotal points 0, 1, 2, 3, 4, 5, 6. Okay. The end load is also calculated by the same way. So it will be in this region. So 5 and 6 are the values. So therefore minus H by 6 into W5 plus 2W6. Okay. So W and W, if you substitute, it will be 3W by 3W into H by 6, which will become minus 0.5 WH. Okay. So next, third step is calculation of the shear force. Okay. So as I've already told you in the method, the steps, first step is to consider a trial shear force. Okay. And then after that, the next shear force will be equal to the previous shear plus whatever point load or equivalent concentrated load which will be there. That one we need to consider. So the next illustrations will clearly let you know how we'll be calculating the shear forces. Okay. Now, after the calculation, at the end of the calculation of the loads, okay, this is the calculation of the concentrated loads. Okay, so this is the end result. You will have P naught and P6 equal to minus 0.5 H. All other values will be 0.5 WH, and all other values will be minus WH, right? Now, we know that calculation of shear force is nothing but W into dx. So, UDL into that interval dx, that will give you the shear force, okay? So, initially, we'll assume a trial shear force, which is nothing but V0L. So, that's nothing but the initial point. So, here, how we will assume this W naught? I've already told you. Okay, this trial shear is nothing but, the total load will be equal to 6 W into L, right? So W into L. So that will be equal to W into 6H. Okay, so 6WH will be the total load acting on the beam. Okay, but here the shear is nothing but we know how to calculate a support reaction in case of simply supported beam with UDL, right? So it's nothing but WL by 2. So W into L will be 6WH, okay, 6WH divided by 2 will give you 3WH. So that is what we are considering here. But actually speaking, in our case, it is a exact answer that we know. Why we calling it as a trial? I'll let you know, because since it is a UDL, you know exactly how to calculate, and I've already mentioned in the last class. So if it is a UDL, I mean, if it is a load which is irregular, okay, like this, if it is very irregular like this, okay,
Yes.
so then it will be very difficult for you to calculate the value over here. That is why we are calling it as a trial. Okay. So even you can consider even different answer also. But if you are considering the different answer, how to proceed, I'll let you know in the next problem. So in this problem, we will not be doing it. Okay. So we'll only be considering the exact answer with the exact answer. Right now. So trial shear. Next, as we know, for calculating the next shear force, what we need to do? Previous shear force plus the P naught, whatever load which will be there after the section, that. So we need to consider both. So therefore, W V0L and the next P is P naught. So therefore, if you calculate it, so you will get the shear force as V0, right hand side. So what I will be doing is shear left to the section we will be considering. So shear right to the section will be equal to V0 plus P naught. Okay, because this is acting downwards,
Minus P naught.
so you'll be getting minus. So it is minus. So therefore, 3WH will be going upwards. That is trial shear. Downwards, the load, concentrated load. So P naught. So that will give you 2.5 H. Okay, WH, right? That is the WV0R. V0R. That's nothing but the shear at the right hand section. Next. So in order to calculate the shear at point number 1, what we need to do, we need to consider these together. Okay, so these two together, and the formula will be given by V1 is equal to V0, because the previous one value will be V0R, then plus P1. Okay, that's nothing but P1 is acting downwards.
We lost P1, so there will be minus P1.
So therefore, yes, negative. So 2.5 V0R will be 2.5 WH, and P1 value, we know that all intermediate values are 1 times WH. So that will give you 1.5 times WH. So that will be acting upwards, because the final answer is plus plus. So therefore, that will be acting over here. Okay. So after the section, so shear, we are calculating shear at point number 1. So it will be acting at point number 1. So next, how to calculate V2? Because we have finished with the calculation of shear over here. We need to calculate next the shear force at point number 2. So in order to calculate point number 2, what we need to do is we should consider the previous shear, which is nothing but V1, and next load. Okay, this way. So we have to consider the previous shear. That's nothing but V1, and the next load is P2. So therefore, Now shear force is nothing but the difference of it, right? Or summation of that. So if we need to consider these together, therefore the formula V2 will be given by V1 minus P2, which is equal to 1.5 WH minus 1 time WH, which is equal to 0.5 WH, right? Now, okay, where exactly it will be acting? That shear force 0.2. So V2 will be acting at 0.2. Maybe just right,
Right,
okay?
all fine.
Next, so similarly, we need to consider V3. We now to
Yes,
calculate V3. What we need to do? We need to consider the previous shear. That's nothing but 0.5 WH. That's
V3
also
equal to
positive, so upwards. And the next W, I
P3.
mean P, concentrated load. So
Yes,
those together, if you consider, right? So you will get a shear force at 0.3. So that is given by V3 is equal to
this
minus
plus
0.5.
minus
So
minus
you
two.
can, and since it is negative, it will be acting downward. So V3 will be equal to
All
V2 minus
right.
P3, because P3 is greater than V2. So the final value will be negative. And that shear force acting, that will be a negative shear force, and it will be acting just with seen in the figure. Next, for finding out V4, we need to consider previous shear force. Okay, that is nothing but V3. And the next joint load are the concentrated load, equivalent load. And then there's those together. If you add them up algebraically, you will be getting V4. So V4 will also be acting downwards since it is also negative. So similarly, we'll be considering for finding out V5, we should consider V4 and P5, and together if you consider V5 is equal to minus 1.5 WH minus WH, which is equal to minus 2.5 H. The last value V6, if you want to calculate, we should consider V5 and P6 together. Okay, so if you sum it algebraically, you will have to get, you will be getting this value, which is nothing but minus 3 WH. Okay, so minus
Okay,
2.5
sir.
WH minus 0.5 WH, which is equal to 3 WH. So this is how we'll have to calculate the shear force. Understood, all of you? Yes, no?
Yes, sir.
Yeah. So now let us move on to the next point. Or before that, see these steps I've just illustrated. I took maybe 1 day to prepare one single slide. Okay, those two above and this one, two slides. Okay, this is just to make you visualize how the shear force and the equivalent forces will be there. But actually speaking, the calculation of that is very mechanical. I'll show you the steps. Okay, that's V6. And for calculating that, okay, you can just draw a table like this very simply, and just consider all the forces. Okay, so we have all the shear forces as previous steps. You have calculated this. I mean, 1 second. So we have only values of P is you have, right? So P is 0.5 WH. So multiplier is WH and 1 WH. Which, what do? You just prepare a table like this. Okay. Initially, only you have this row. So minus 0.5 H minus 1 WH minus 1 WH minus 1 WH. With only these values, very easily you can calculate shear force. I'll show you how. Okay. So 0.5 H WH 1 WH 1 WH and 0.5 WH. So you have written this. Okay. Now to find out the shear force over here, this is the trial shear that you need to assume. So the other values will not be there initially. Okay, they will be not there. Now for finding out the shear force here, V0 right hand side. Okay, this is called V0, and that can be obtained by 3 minus 0.5. You just arrow mark, you can see initially this is the trial value. You just put it over here. Okay, you will write initially, so these won't be there. Okay, these won't be there initially, so you will start from here. So 3 minus 0.5, it will be 2.5. It will give you 2.5. Okay, next, so in order to calculate V1 shear force over here, okay, what you need to do, this previous shear force, okay, whatever value you get, you just sum it with the load. That's nothing but 2.5 minus 1 WH. You will get okay 1.5. Similarly, 1.5 minus 1, you will get zero point 0.5. Okay, as you can see, 1.5 minus 1.5. Similarly, zero point 0.5 minus 1 minus 0.5, isn't it? So zero point 0.5 minus 1 minus zero point 0.5. Next, minus 0.5 minus 1 minus 1.5, right? Similar, next, minus 1.5 minus 1 minus 2.5, right? The last value minus 2.5 minus 0.5, we will get it equal to minus 3. Okay, minus 2.5 minus 0.5 will be minus 3. That will be the final shear force you're going to get, right? So these are very simply you can get it. So all those explanation I had given in the previous slides is just for your illustration purpose. Okay, now let us calculate the bending moment, calculation of the bending moments here. Okay, so in order to calculate the bending moments, so according to Newmark, the bending moments are just addition of shear forces, successive shear forces. Okay, what you need to do here for finding out what you need to think is you need to initially assume a trial bending moment. Okay, so assume a trial bending moment over here. Then the bending moment at 1 will be nothing but previous bending moment plus 0.25 WH, 0.25 W. Okay, 0.25, sorry, 2.5, and the multiplier will be actually WH into H. You will get it as WH square. Okay, so WH square here. So you will get it over here, right? Next, similarly, bending moment at second point will be obtained by 2.5 plus 1.5 WH square. Okay, so 2.5 which is there plus 1.5. You just need to add the shear forces. Okay, previous shear force, these successive shear forces up to here. So 2.5 plus 1.5, which will give you 4. Now next thing is the last bending moment plus the next shear force. Okay, the last bending moment is 4 plus 0.5, that will give you 4.5 WH square. Okay, so what we'll be doing here is initially previous value will be WH. Okay, because the same load will be considering. The next one bending moment will be into the length, right? So we'll be multiplying with one more H, right? That's all. So whatever shear force which will be there into H will be doing. So that's the reason why it will be WH into WH square unit. So this is the multiplication factor. So these are the only values which will be written in the table. Now, so therefore M3 you got it as 4.5. Next, to get M4, what you need to do? 4.5 plus the next shear force. We need to cancel 4.5 plus next shear force, which is nothing but minus 0.5, which will give you, so 4.5 minus 0.5, it will be 4 WH square. Okay. Similarly, next we got this value. Next is to get M at 5, moment at 5. So moment at 5 will be equal to 4 minus of 1.5. It will give you 2.5. The last value will be, so 2.5 minus 2.5, which will give you 0. Okay, so this is how you will have to calculate the bending moment values in the beam. Okay, so thing is here, since the trial shear whatever is there, how do you know this is 0? How do you assume this? Anybody? Anybody? Hello?
Is equal to 0.
Yeah, since it's a UDL, definitely you
UDL
know
first point
that the bending
is
moment at
related
the
0,
support
sir.
will be 0, isn't it?
0.
W not P not.
Yeah, bending moment at the support
Yes,
will
sir.
be 0.
Yes.
So from boundary
Yes.
condition, you need to assume. So hence it will be 0 only. So you can easily assume. So next we will move on to the next point. Okay. So we got bending moment and shear force. Next for calculating slope and deflection. Okay. So what you need to do is you need to load the given beam. Okay, this is the given beam with moment M by I diagram. Okay, so that's nothing but this is the moment value you got actually. Moment is equal to 0, 2.54 and 4.54, 2.5 at 0 at points. Okay, 1, 0, 1, 2, 3, 4, 5, 6 now point numbers. Those are the values. Okay, what you need to do is you need to draw a M by I diagram on the beam. Taking these as the moments, draw M by I diagram. So multiplier will be WH square divided by 4. These values 2.5. So here it is 0, 2.5, 4, 4.5, 4, 2.5 and 0. So this is the M by I diagram. Now what you need to do is you need to consider this as the load. Okay. So moment the M by A diagram, uh, whatever is there, this has to be considered as load onto the beam. Okay. And the same procedure which we did in the previous case has to be followed here. Okay. So the thing, this is the formula we will going to use. Okay. Um, so now what you need to do is you need to you should start from the beginning, like how we calculated the shear force. I mean the equivalent point loads and the shear forces and bending moment. The same procedure you need to follow or repeat here, considering instead of UDL, you will be considering M by EI diagram as the load. That's all. Okay. So there the UDL, the load was straight line. Okay. The variation was straight. But here the variation is parabolic. Okay. So for parabolic, I had previously given the equation for the equivalent loads given as H by 24 7W0 plus 6W1 minus W2 into WH square by I. Okay. This is the formula. Okay. A multiplication factor. It will be the multiplication factor. That's it. Okay. So I've given that in previous case. Okay. Just to show you. Yeah. So this is the formula. H by 24 7W0 plus 6W1 plus W2, and multiplication factor will be there because we are not considering the values. Okay. So that will be there adjacent to it, because we have considered only uh, yeah, here we have considered only the values 2.5 and all. We'll be considering this as the W naught, and this is W1, W2, W3, so on. This will be there adjacent side multiplication factor. So outside the formula. So therefore the formula is given by H by 24 7 W naught. By using this, you calculate P naught, which is nothing but 0.45, all those things, 0.45 WSQ. If you simplify it, so here the value will be W naught will be 0, W1 will be 2.5, okay, W2 will be 4. Just substitute, you will get P naught equal to 0.45 WH square by WH cube by EI. Similarly, P1, which is nothing but acting over here, okay, P1 load acting over at point will be nothing but the formula will be given by uh, W naught plus P1 will be equal to, actually this will be W1 plus yeah, W naught plus uh, yeah, W1 plus W2. Okay. So correct. The formula is correct. H by 12, W naught plus 10 W1 plus W2. Substitute them because W naught is 0. Okay. And 10 W1 2.54. Just like this, you calculate P1. P2 also you will get it 3.91. And P3 will also be there, which is equal to 4 something, 4.41 in WH cube. Okay. All these values are H cubes. Okay. Yeah, H square. The final answer is H cube. Okay. So there is a mistake over here. This is H cube. This is H cube, and this is also H cube. And we know that by symmetry, P4 will be equal to P2, which is equal to 3.91 WH square by 4, and P5 is equal to P1 2.41 WH H cube by. These are also equal to W cubes. Okay. WH cube by EI, WH cube by EI. Okay. So we have calculated the equivalent point loads. Next is to find out the slope and deflection. Okay. So these are the equivalent. Considering M by A diagram as the load, we have calculated the equivalent point loads. Okay. And next thing is to find out the slope and deflection. That's nothing but shear force and bending moment using these loads. Okay. That is what you do in moment area method, right? In moment area method, what do? You will consider M by A diagram as the load, and you will calculate the area. You will get the bending, I mean shear force, and moment of the area will give you bending, deflection, isn't it? So the area of the M by A diagram will give you slope, and moment of area of that about the point will give you bending, the deflection. That is what you're going to do in the step. Okay. So here same way what you need to do, you just write down all the values 0.45, 2.4 and all, P2, all these things, you write it over here. So you need to do a trial value here. Okay, you have to consider the trial deflection here. Okay, so how do you calculate the trial shear, trial slope here? So what do you mean by trial slope? Trial slope is nothing but actually the that you need to calculate from some value you need to assume, that you can assume by considering yeah, you need to consider we know that the deflection is given by area. So the total deflection which will be there, the slope at the end, the slope at the end will be nothing but the half of the area. So you calculate half the area of this figure. So half the area will be nothing but what is the formula for area of a parallelogram? Parabola.
Parabolic.
Parabola, area of parabola. Area of the parabola. 2/3 of WH, right? Isn't it? So total area will be nothing but 2/3 of W into. So after you calculate the moments, okay, these are the values which will be there. 0, 2.5, 4, 4.5, 4, 2.5. These are the moments acting, okay, which will be there on the beam. What do you need to do for finding out the slope and deflections? So as in the case of moment area method, M by A diagram will be considered as the load, and area of M by diagram will give you slope, and moment of area of M by A diagram will give you deflection. So the same procedure you will be adopting here. Okay. So what do? You consider moment this as the M by EI diagram. So whatever values of bending moment will be there, you just multiply with EI divided by EI, M divided by EI. That will give you M by EI values. So these are the M by EI values. Okay. So this is actually 2.5 WH square, right? So therefore, here the load will be M 2.5 WH square divided by EI. So that way you consider till the end. So 2.5, 4.5, just nothing but the bending moment diagram, but divided by EI. That's it. Okay. And we know that bending moment diagram, variation of the bending moment diagram in case of UDL is parabola. Okay. So area of the parabola will be nothing but 2/3 of W mid-ordinate into the length. Okay. So that will give you a maximum slope. But we know that the half slope will be this side and half area will be this side and half area will act here. Therefore, whatever support reaction or the total area on the left hand side will give you slope over here. Total slope on the right hand side will give you total area on the right hand side will give you slope here. Okay. So next thing is to actually speaking, so after you find out the bending moment diagram, you have to calculate the equivalent load, because since it is a parabola, in this case you can easily calculate the area of that parabolas. Okay, it will be easy. But if it is a if it is different shape, okay, then finding the areas will be difficult. So we can use this Newmark's method for finding the equivalent loads. Okay, so P naught is equal to H divided by 24. These are the formulas given. Okay, for the last and the last and the first equivalent loads are given by this formula, and the intermediate ordinates will be given by the next formula. I'll show you. So let us calculate. So after you find out the bending moments, so first step is to represent them as M by A diagram. Next, calculate the equivalent loads. Okay, calculation of equivalent loads of M by A diagram. That's the next step. That we did it in the same way we did it in the case of previous value. Equivalent loads calculation we did it right, but the formula only will be different because the variation is not straight line here. So we are using it this formula because it's a parabola. So for parabolic variation, the Newmark has given this formula. So P naught, you just need to substitute the values of W naught, W1, W2. So W naught here is 0, W1 is this one, W2 is 4, W3 is this. So therefore, considering them, substitute the value, and by that you will get 0.45 WH cube by EI. Okay. So similarly, you will be calculating the P1, okay, which will give you 2.4 WH cube by EI. This is WH cube, as I already told you. And this one will be equal to P2, which is equal to W1. Formula is given by H by 12, W1 plus 10 W2 plus W3 into WH square by EI. Okay, there's a multiplication. If you simplify it, after substitution of W1, which is equal to 2.5, W2, which is equal to 4, W3, which is equal to 4.5, in the above formula, we'll be getting 3.91 WH cube. Okay, this is WH cube by EI, because H square into H, it will be WH cube. Next is P3. P3 is equal to H by 12. So for P3, so if you want to consider, so that will, this will be the area which you're going to consider. Okay, so this is the area for P3. P3 will be acting over here, right? P3 will be acting over here. Therefore, the ordinates will be 1, 2, 3. Therefore, it starts from W2. W2 plus 10 times mid ordinate plus 1 time the last ordinate for P3. So substitute those values here, W2, W3 and W4 here. So that's nothing but 4, 4.5, 10 into 4.5 plus 4 into that. It will give you, 4.41 WH cube by EI. So this is also WH cube by EI, right? And similarly, you can calculate P4. P4, because of symmetry, which will be equal to P2. So P2, right? That value is W 3.91 WH cube. Similarly, P5 will be equal to P1, that of P1, and you will get 2.41 WH cube divided by EI. Similarly, P6 will be equal to P0, which is equal to 4.45 WH cube by EI. So this is how you can get the point loads. Then actually speaking, what you the thing is, you can load them as so after you find out the loads, you just write down in the table like this. Okay, so P naught is equal to 0.45 here, and P1 here, and P2. Okay, P2, P3, right? P3 value. So actually this is wrong. Okay, P3 is 4.41, and P4 is 3.3, 3.91, and P5 just like this. You just note down this, and then very simply you need to start calculating the slopes. Okay, this is actually only the loads acting on the beam. Next, we need to calculate the slope. So for finding out the slope, we need to have a trial section. Okay, trial slope initially in the beginning. Okay, we don't know initially. So the Newmark has given the formula for how to calculate the next values, but he has not given how to calculate this, the first value, because it's a trial value. You don't know. See, in our case of UDL, you can find out UDL. In case of UDL, it's nothing but we have a point load sorry, if you have a UDL on the beam, okay, like this, and we know the bending moment diagram will be parabola like this. Okay, and M by A diagram also parabolic. So this will be, assume that this is M by A diagram. Okay, just like this, you will have number of ordinates. Okay, so this will be M by A diagram, and so the initial slope which you're going to get, actually slope is nothing but you will in the beam, the beam will bend like this. Okay, this is the supports, actually support reactions which are there at the end. Slope is nothing but the tangent drawn to the elastic curve. Okay, so this will be the slope over here which you need to calculate, right? You just consider that as 5. So according to moment area method, so because we need to assume some trial value, right? We have some formula. It is nothing but, so total area is nothing but total slope. So the slope over here will be nothing but half of the area of this parabola. Okay, so total parabola is this. So half of the area of the parabola will give you slope over here. That value you can take it as the trial value. So can you calculate the half of the area? So which is nothing but the maximum ordinate is actually 4.41. Okay, just all of you try this. 4.41 WH cube. Okay, this is H cube, right? WH cube, you just take it like that. WH cube. So it's nothing but half of the area. 2/3 of 4.41 into 3h. This length is from here to here. It will be 3h. Yeah, can anybody calculate for me? 4.41 into 2/3, 2/3. Okay, into 3. How much it will be? 2/3 of 4.41. So it's almost this 3 will get cancelled, isn't it? So which is number 2 into 4.4 something. It will be around this value only, right? 8 point something you will be getting, right? So that's how you will have to assume a trial value of the slope. Okay. So after assuming the trial value, then the process is very simple. So as we did for calculation of the shear force, what it will be the initial slope and then summation of this. Okay, and we know because here we will be assuming the slope as negative. Okay, here we'll be assuming the slope as negative in the beginning. Okay, so therefore the final slope will be yeah, this is the initial slope. So next slope at the next point will be nothing but this plus this, which is nothing but minus 8.98 plus 0.45. It will be equal to minus 8.53. Okay, now slope at the next point, at point number 2, will be obtained by, okay, yeah, so slope at the next point here, so will be obtained by previous slope plus the equivalent load. Okay, so that will give you minus 6.12. Similarly, the next slope will be obtained by the previous slope plus the equivalent load. So which will give you 2.21. Similarly, previous slope 2.21 plus minus 2.21 plus 4.41. You will get it equal to plus 2.1. Similarly, 2.2 plus 3.91, it will give you 6.11, and 6.11 plus 2.41 will give you 8.52. 8.52 plus 0.45 will give you 8.97. Okay, so this is how you will calculate the slopes at different points in the beam. Next, we need to calculate the deflections. So deflections are nothing but the same way how we calculated the bending moment. We need to calculate here as well. So how we did bending moment, it's nothing but summation of the shear forces, previous shear forces, isn't it? Plus the previous bending moment. Okay. So now we have to assume the initial because we know in case of deflection at the support will be 0 only, right? So that's boundary condition. From boundary conditions, you should assume the initial deflection. Okay, at the support, the initial deflection is 0. So therefore, the next the deflection will be nothing but previous deflection plus the slope value. Okay, so it will give you minus 8.53. Next, the next slope, I mean next deflection can be obtained by previous deflection, what we got now, plus the next slope. Okay, so therefore minus 8.53 minus 6.112, you will get minus 14.45. That is acting downwards. Okay, downward deflection. Okay, so negative, that's the reason why we are considering as negative. Next, so for the next deflection, that's nothing but maximum deflection at the center. Okay, you can get by the previous deflection plus the next slope, the way with which we had calculated the bending moment, same way. Okay, that will give you minus 16.86. Now, Okay, the next deflection you can get it by the previous deflection plus the next the slope. Okay, at slope at that point, 3 point. Okay, just that way you can go on calculating the deflections, and that gives you minus 14 point something. Then again previous deflection plus the next slope will give you next deflection, and this deflection with the next slope addition to that, you will have to get 0. There should be 0 error. Okay, so this is how you need to get the the slope here and the deflections over here. Okay, very simple. Okay, and the multiplication factors, each time it will be multiplied by h. So the equivalent joint load will have wh cube by ei, and the same will be there for slope, whereas it will be one time h for the next point. Okay, one more times into h will give you the deflection or the deflection equation. Okay, so the maximum deflection is given by minus 16.84 wh to the power 4 divided by ei. Okay, that's the value. So if you wanted to check the value, so what is the actual deflection in case of beams with the UDL? Anybody? What is the maximum deflection in case of UDL, beam with UDL? Hello? Yes, anybody?
3
WL cube by 8 to the power 4 by
5 by 384 by EI.
5 WL to the power of 4 by 384 EI, isn't it?
4 divided by 384
EI. Just calculate the value. Okay, some decimal value. Similarly, here the value of H you substitute equal to L by 6. Okay, and you will get the same value. Okay, you can do the cross check on your own. Okay, so this is nothing but 16.86 divided by EI. Okay, so what do? You just consider H is equal to L by 6, right? Or what you can do is minus 16.86 divided by 6 to the power 4. What is the value you will get? You just see. So you can calculate 5 WL cube by the 5 WL to the power of 4 by 384 EI. So 5 divided by 384, how much you will get? Calculator. 5 divided by 384. It's nothing but 0.013. Are you getting it? 5 divided by 384. 0.013. Now, in our case, it is 16.86 divided by 6 to the power 4, because H is L by 6, right? So L to the power of 4 by 6 to the power of 4. Therefore, 16.86 divided by 6 to the power 4. How much you'll get? 16.86 divided by 6 to the power 4, and it is same as that. Okay, 0.013. Are you getting it? Anybody tried? 0.013 only you'll get it. Okay, I'll just show you the I'll show you the other screen. I'll share the screen as some Excel sheet. I'll share our calculator. Okay, that calculator cannot be shared. I'll share the Excel sheet. Okay. Yeah, everyone, I'll be sharing the Excel sheet now, right? Excel. I don't know, it's not shared. Okay. Can you see the screen? All of you? Hello?
Yes, sir.
Yeah, so I'll present now 5 divided by 384. Let's see, 5 divided by 384, which is equal to 0.0130, right? Now, in our case, in this case, actually, the maximum deflection is given by 16.86 WH to the power 4 by EI. So here H will be equal to L by 6. So 6 to the power 1 by 6 to the power 4, or 16.86 divided by 6 to the power 4. The same thing we will do here. So 16 point, you can see the previous answer, you just note down 16.86 divided by 6, one more time, divided by 6. Okay, divided by 6. So I've just divided 4 times, you can see. So previous answer was 0.0130, and then so now the answer is 0.0130. Last digit little different is there. So understood. So this is how you'll have to calculate slope on deflection using the Newmark. Thanks for watching. Like, share, subscribe, press bell button for latest updates.